Hi, if you've been paying attention to space news this year, you might have noticed that one spacefaring nation has been noticeably absent. This year, not one orbital launch has occurred from Japan. In the first few months of the year, JAXA was preparing to launch the H-3 rocket, Japan's new flagship. This rocket has been delayed due to technical issues for years now, and this time it seems to have stopped anything from launching from the Tanegashima Space Center at all, including the last few remaining H-IIA launches. I'm AI Kuni, and today I want to talk about the H-3 rocket and why it's been delayed for so long. So the H-3 rocket is a much larger rocket than the H-IIA, Japan's previous flagship. It's also larger than the H-IIB, which has only ever been used for the HTV. It's kinda weird though, because the H-3 is a lot weaker than the H-IIB. The H-IIB can haul 8 tons into geostationary transfer orbit compared to the H-3's 6.5 tons. That's certainly a downgrade, although it's still a bit more powerful than the H-IIA's 6 tons. If the H-3 rocket is bigger and weaker, you might wonder, like I did, what the point is. Well, it turns out that the H-3 is a lot cheaper. JAXA has struggled with the large launch costs associated with their rockets since forever really, and they want to turn that around, especially now that competitors like the Falcon 9 have tanked launch costs. The aim was to make the cost to launch an H-3 on par with that of a Falcon 9, so where the H-IIA would cost $90 million to launch, the H-3 would only cost $50 million. This is almost half. How can you make a larger rocket cost so much less? Minimizing changes in tank width is one way, as is increasing launch cadence, that way you can bank on economies of scale more easily. They also use some 3D printed components, and I bet they found more ways of shaving off tiny amounts of costs here and there, but the most important factor is going to be the engines. The H-IIA and the H-IIB make use of the LE-5B engine on the second stage. The H-3 will make use of a slightly upgraded variant of the LE-5B, which is slightly cheaper. The biggest difference is in the first stage engines. The H-IIA and the H-IIB make use of the LE-7A engine on the first stage to hoist the rockets off the ground. The H-3 will make use of the brand new LE-9 engines. They're a sort of upgraded form of the LE-5B engines, but to explain exactly how these engines are better, I first have to explain a bit about how engines work in the first place. For a rocket engine to fire, you need to somehow pump the fuel and the oxidizer, or hydrogen and oxygen in the case of the Japanese rockets, into the combustion chamber. This is generally done using a turbine powered by the same fuel that you're using to get off the ground. The LE-7A engines on the H-IIA and B are staged combustion cycle engines. What this means is that the hydrogen is first pumped into a preburner together with a small amount of oxygen. A small amount of the hydrogen can then burn up to provide the energy to power the turbines. The remaining hydrogen is then pumped into the combustion chamber. And we have liftoff. The LE-9 engine is much simpler. It ditches the preburner and instead gets the energy for the turbine by cooling down the engine. As hydrogen boils at 20 Kelvin, it's ideal for cooling the engine, something which has to be done regardless. Now where in the LE-7A engine you'd want to avoid having the hydrogen boil off, in the LE-9 engine that's exactly what you want. As it boils, it expands and you can use this energy that the LE-7A essentially wasted to power the turbines just fine. The LE-9 engine is then referred to as an expander bleed cycle engine. The bleed part refers to throwing the fuel overboard once it's finished powering the turbines. Now it turns out there have been some issues getting the LE-9 to cool down properly. How it's supposed to work is as follows. A valve opens to let the hydrogen cool down in the combustion chamber, the hottest part of the engine, after which it's piped to a second valve which controls the cooling of the engine belt. More importantly, it controls the thrust. The further it's open, the more hydrogen passes through the turbines, the faster the fuel can be pumped into the engines. Now as it turns out, the heat was too much for the combustion chambers, and the walls were perforated because of it. And sadly, that wasn't the only problem with the LE-9 engines. Vibrations on the turbine fins are at exactly the wrong frequencies, causing resonance. Mechanical equipment doesn't tend to like resonance, so they get damaged. Cue the that one video? Yeah, that one. If the turbines don't work perfectly, you can't get the thrust you need out of these engines, and as I'll get to in a bit, you need every newton of thrust you can get. Without functional turbines and combustion chambers, you're not going to space today. And so, Mitsubishi Heavy Industries has been working tirelessly on redesigning the turbine fins and the combustion chamber, and designing equipment to specifically measure the resonance and the wall temperatures. Once they finish developing these engines, the LE-9 engines will be engineering marvels. It will be the most powerful expander cycle engine ever built. Expander cycle engines like the LE-9, but also the LE-5B and the RL-10 engines, which you may know as the engine that powers the SLS upper stage, will range around 100 kilonewtons of thrust each. The LE-9 engines, however, aim to get a thrust of 1,471 kilonewtons, which is really needed to get that thing off the ground. The second strongest expander cycle engine under development is Blue Origin's BE3U, which with 710 kilonewtons is less than half as powerful as the LE-9 will be. I cannot overstate how amazingly powerful that is for the engine type. But you will need it to be much more powerful than the rest, as the engine type has never been used for the first stage engine before. The H-3 rocket isn't the only thing they managed to make a lot cheaper. The HTV successor, the HTV-X, is also a lot cheaper, and more importantly for the H-3, a lot lighter. The H-IIA was just 1.5 tons short of getting the HTV into LEO, while the H-3 is more powerful. It's not that much more powerful, but enough to make the cargo capacity of the HTV-X 2 tons more than the HTV's 4 tons. And fully loaded, it will still be a full ton lighter. This was achieved by cutting down on thrusters, batteries, and a lot of dead weight, but that's a story for another time. I do hope that the H-3 will fly soon, and Japan can get back into space as soon as possible. The engines are being tested, so who knows when it will happen. The first flights of the H-3 will carry Daiichi-3, an Earth imaging satellite with a 0.8 meter resolution, a lot better than the Daiichi-1's 3 meters, which it will come to replace. They will also carry a multispectral imager, which is useful for example, agriculture and nature preservation. The HTV-X will be launched on a later rocket, though parts of it have already arrived on Tanegashima. When it inevitably happens, I will be here on this channel to cover the launch, so subscribe to see when it happens. Until then, I'll see you next time. Bye!